Hi everybody, this is AP Stats 8.3 notes. So remember yesterday or the last time we did notes, 8.2 was on proportions. So now we're going to do the same thing, creating confidence intervals for means. So remember, means could be things like the average length of something, the average width of something, the average count of something, right? Anything that would basically be a number, not a percent. Okay, so in order to do confidence intervals on means, we need to be able to find all the values of the formula. So just like the regular confidence interval for proportions, we start out with what our guess is from our sample. That's called the statistic. So in our case, since it is means, it is going to be X bars. Okay, then we're going to do plus or minus a critical value. For proportions, that was Z star. For means, it'll be Z star or T star. We're going to talk about the T in a minute here. So I'm going to put either one. Okay, and then the standard deviation of the statistic. So the standard deviation of the statistic is usually in means it is sigma over square root of n. And we're going to talk about how that might change this time as well. So there's more going on with means than with proportions. Proportions are fairly straightforward once you get the hang of a confidence interval formula. Okay, so that would mean we're trying to guess, right? We're trying to give them a guess at what we think the mean is, plus or minus some amount of error. But our formula says that in order to make the guess, we have to know sigma, which is the standard deviation of the population. Well, if they knew that, why would they have us guessing what the mean is of the population? If they knew what the spread of the population is, it doesn't make any sense, right? So if they're really asking us to estimate a mean, we're not going to have sigma, right? We're going to have something else. And that's what causes the difference between the Z and the T, is whether they gave us sigma or not, all right? So underneath here, let's write. So if the problem, for whatever stupid reason, right, if the problem gives you sigma of the population, then you get to use a Z star score, just like we did for proportions. But if the problem, sorry, I need to fix that to say if the problem gives you just the standard deviation of the sample, then we're going to have to switch over to a new distribution called a T star score. Okay, so let's talk about how that changes a little bit. Well, if we're going to use a T star score instead, we're going to also have to know one other piece of information, and that is degrees of freedom, which you just calculate by sample size minus 1. Okay, so sample size minus 1. Take a look at these two dot plot distributions. The top one is using the T and the bottom one is using the Z. And what you should notice about both of those is both of those look like they could be approximately normal, right? So when we go check conditions, we're still going to check the normal condition to see if they just have that general shape of that curve. But it's not going to be exactly the same for a T, right? And also notice that the T is more spread out. It's got more points coming all the way out here than the one with the Z does. The Z is much shorter, right? And then the other thing notice is that in the T distribution, it is lower in the middle than it is in a Z distribution. Okay, so that is taking where we actually look at a whole bunch of samples. All right, so let's show you honestly what the graph looks like differently if we were to smooth it out and take a look at it. All right, so let's see. In the normal one is the purple one right here. So this is our normal one. This is the one that has the 68, the 95, and the 99.7% distributions, right? For 1 standard deviation, 2 standard deviation, and so on. If I'm using the T distribution, what's going to happen is, let's look at one that has very, very small sample size. So like a sample size of 2, right? So 3, so it has 2 degrees of freedom. And that's going to be kind of this reddish orangish one, right? So that would mean n was equal to 3 and we've got 2 degrees of freedom. And what you can see about this one is right here, it is definitely higher than the Z distribution. Over here on this tail, it's higher. And then in the middle, it's actually lower. So a t distribution in general is not as high in the middle, but it is higher on the tail ends. Okay. If I increase the degree of freedom, which just means increase the sample size, what do you notice here? So now we had an n is 10, right? And now notice that it is moving towards, it is still lower in the middle because it's a t, it is still higher on the tails because it is a t, but it is getting closer to, gets closer to the normal distribution. So the bigger the sample size, the more it is actually going to start to look like a z-star score anyway. So if we know that they did not give us a standard deviation of the entire population, we're still going to check the normal rule anyway, because it's going to be relatively close enough for us to know it's going to make this shape. And then we also know that if the degrees of freedom get high enough, it's going to approximate a normal curve almost exactly, right? As long as the sample size is big enough. Guess how big it needs to be for it to approximate a normal curve? If you guess 30 from central limit theorem, you are correct. By 30, it's going to look like the other one, and it really would not matter. Okay, but again, for our purposes, it's all based on that sigma, that standard deviation. If they give it to you for the whole population for whatever stupid reason, then we can do it a z-star. If they don't, and they only give a standard deviation of the sample, that's S sub x, then we have to use this new t distribution. That's going to be a little bit higher in the tails, a little bit lower in the middle. Okay, all right. So that means as the degrees of freedom increase, the t density curve approaches the standard normal curve ever more closely, right? Gets closer and closer. So let's use this as an example so that you can kind of see what we're doing here. So just like we did with z-scores, we started with the table in the back of the book. Now the difference is, notice that now we are using a table B, which says it is a t distribution, and I can notice on one side that there are degrees of freedom listed, and over here they just want the tail probability. Okay, they don't need the whole middle amount, right? They just need the tail. All right, so in our first one, they want us to find the t-star score for a 90% confidence interval based on an SRS of size 10. All right, so let's go and draw that. So just like we would have normally done for a z, we're going to go draw our 90. We're going to say this is 90. And that leaves us 10 to split out. So this is going to be 0.05, and this is going to be 0.05. So now notice that I also want to look for the tail probability. So I'm looking for, in green, I'm looking for this one right here. And I'm looking for a degree of freedom of n minus 1, which is going to be 10 minus 1, which is 9. So I'm looking at this row and that column and where they come together to match. My t-star score is going to be 1.833. Right? So this would have normally been the number that you would have gotten from inverse norm. So this is the way we use it in our table. Okay, and this table is again in the back of your booklet. Just look for it to say table B, but more importantly, it just should say t distribution critical values. Okay, let's try that one more time. This time we are going to use a 99% confidence interval. So in a 99% confidence interval, 99 in the middle, that leaves me 1% to split. So that's 0.005, 0.005. So again, looking at the top, 0.005 is this one right here, this column. And then for degree of freedom, it's 95 minus 1, which is going to be a 94. So I took a picture of the bottom of the table, so we weren't trying to look at the whole thing. And notice that after a while, they don't give us every single one, right? So I can see that it's between 80 and 100. And we are always going to round down because it's going to give us a bigger t-score, which is going to give us a bigger confidence interval. It's going to spread it out more. So instead of using the 100, we're going to use 80. So we're going to use degree of freedom 80 in our table and working our way all the way across the 80 row until I hit this arrow. It looks like we're going to get a t-star score equal to 2.639. So then that would just go in where we used to put the z-star. Okay, now there is a way to do this on our calculator, and again, it depends on the type of calculator you have. Some of the older, even the TIs, do not have this function. So this is one that's really important to just know how to use the table And then we want to make sure if we have to use the table because our calculator doesn't have it, that we are telling them we use the table to find the T-star score, not our calculator. So let's go back and we're going to redo this with the calculator. We're going to show you how to do it. So I'm going to go back to the green one. And in the green one, we're going to be doing inverse T. Okay, and then your calculator wants the middle and the right-hand tail. So on this one, it would have been 0.95, I think, 0.95. And then it'll want degree of freedom. So degree of freedom would have been a 9. So same place where you would have found inverse normal. Don't be surprised if it's not there. It is not there on a lot of calculators. So right underneath inverse norma, my calculator, it's number 4, inverse T, and it asks for the area. So I'm going to do 0.95, and I'm going to give the degree of freedom of 9, and then I'm going to go ahead and hit paste. Okay, and in my calculator, I am getting a T-star score of, for the calculator, is going to be 1.833. So this one is almost exactly on. Okay, so when I go and check the red one, I'm not expecting it to be exactly on. So that's going to be inverse T, and this one is going to be 0.995 with a degree of freedom of 94. So again, second bars, number 4, inverse T. If you don't have it, you're going to have to use the table in the back of the book. So this one is going to be 0.995. Degree of freedom is going to be 94. And when I paste this one, calculator T-star is going to be 2.629. So notice it's a little bit smaller using a calculator because the table really wasn't able to give us the 94 exactly. And so we created a T-star that makes the confidence interval a little bit wider. So the 0.2639 makes it a little bit wider than the 2.9. Cool. All right, so let's go through how to run a confidence interval for means. We're going to use the same conditions. Now on your piece of paper, this one should already be in there, but I'm going to rewrite it on mine so that it's here. Is after random, we're still checking random, right? We want to see that it's either coming from a random sample, right? So that means randomly selected. So this is selected, or a random experiment that would be randomly assigned, right? So usually I've been telling you just look for that word random and you could say it was stated. The other thing that's on your paper that's not on mine is the 10% condition for independence. Okay, and that's still the 10 little n has to be smaller than big N. Okay, and again, where n is little n is sample size, big N is population size. All right, and then for normal or large samples, we're still using, basically, we are hoping that they tell us that the population has a normal distribution. That's our number 1. Once it has that, I don't have to check anything else. Second is I'm going to go to central limit theorem, just like I have in the past, right? As I'm going to see if my sample size is more than 30. Let's say that it's not. We're going to add in a new section now. If it's not, we want you to draw or create or look at, if they provide it, either a dot plot or a histogram. Okay, and what we are really looking for is we are looking for if there's strong skew or outliers, then we have to stop. We can't assume normal, which means basically if we were doing a panic problem, we would stop the whole panic problem, the whole interval, and we'd stop. Okay, so most of them, if they're expecting you to do an entire write-up to find the confidence interval, it's going to pass that if you go and look at its dot plot or if you go create its histogram. It should not have any strong skews or any major outliers. And basically then we're just going to say, it looks good enough, we're going to continue. There's nothing majorly that makes us not think this will go normal. Okay, so the rule still is n being higher is always better, that the higher the sample size, right? We expect that the mean would be unbiased and that the higher the sample size, the more accurate our standard deviation is, right? So that as n increases, standard deviation or spread decreases, right? So this one is going to be a biased estimator. I'm not going to get the same standard deviation for the population as I am for a sample of different sizes is going to give me different standard deviations. All right. All right, so let's go through an example of checking to see that extra thing for whether we can assume it's going to go normal or not. All right, so in our first one here, it says, can we use a T-star critical value, right? So we want to estimate the average time in minutes. That's definitely a means problem, not a percent problem. To order and receive a regular coffee at a local coffee shop. The time for 5 randomly selected. So when I go to check for normal, they didn't say the population was normal, right? Certainly 5 is not going to be bigger than or equal to 30. So then I have to look at the dot plot, and they've already provided it for me. And what do I notice about the dot plot? Right away, I should be noticing that there is an outlier over here at 6, and that it is basically skewed left because everything else is on the left. So on this one, we would say, that because we can't assume it's normal, can't assume our sampling distribution is approximately normal, and we basically have to stop the problem. So stop doing the confidence interval at that point. All right, here's one that hopefully looks a little bit better for us. Let's take a look. Okay, so this one is a middle school counselor wants to estimate how many minutes on average students spend doing homework. The histogram of the amount of time doing homework is below with a sample of 20 students. So again, they didn't say the population was approximately normal that they selected from. The central limit theorem will not qualify, so it doesn't pass central limit theorem. So then we look at the data that they gave us. So they've already provided us with the histogram. I'm not seeing any outliers. These gaps are almost all the same everywhere, right? That's not heavily skewed. It's looking pretty good. So we're going to basically say no strong skew and no outliers. Means that we will assume sampling distribution is approximately normal and continue. So we continue the problem at that point. So you can see, even if central limit theorem is not met, we're still going to look at it, because if they're asking you to do calculate an interval, they really want you to get that far. So even if their sample sizes are super small, I mean, good news is they're super small, the calculation should be easier, right? We're still going to look at them and we're going to try to say we can continue. Okay, that is our main goal, is that we're going to be able to continue. All right. All right, so here is our calculation again of how to find the interval. We start with our statistic, so that is our X bar, right? And then we're going to use a T-star, and we're going to use standard deviation and N. So remember that T-star and S go together, T-star and S, and then Z-star goes with if they provide you sigma. So you're going to have to read about, did they give you the standard deviation of the sample, or did they give it of the entire population? All right. All right, so some of the words are also changing here. So let's talk about some of these words that are actually changing. It used to be that this amount right here was called standard deviation, right? Well, if we're using sigma, it is standard deviation. If we're using a guess at what sigma is, it becomes a standard error. Remember, another name for error is variability. So it's now got a standard error or a standard variability of the sample mean because we had to use a sampling version of it instead. Okay, standard deviation is still that S sub x at the top, but S sub x over square root of n is now called standard error. Margin of error is still the same. It is everything after the plus minus. So all of this counts as margin of error. Okay, so the T-star, then the S sub x over square root of n. And then we have to remember that anytime we're using T star, we're going to have to go calculate the degree of freedom, okay, which is n minus 1. Awesome. All right. Anything else? Let's go through and do an example all the way through and then we are done. All right, so for a second semester project in AP Stats, Ann and Tori wanted to estimate the average weight of an Oreo cookie to demonstrate the average weight was less than advertised. So they think they're getting ripped off by the Oreo company and the weight of the cookies. So they select a random sample of 36 cookies. So I'm going to start going through here and I'm going to start marking stuff up, right? So I can see they did random. I can see 36 cookies is going to be my sample size. I can see that the mean weight, they actually labeled it for me. That was very nice of them. And that their standard deviation of their sample, they also labeled that. That was very nice of them, was 0.0817 grams. So they want me to construct and interpret a 95% confidence interval for the mean weight of a Oreo cookie. Okay, so the first thing is we want to identify our parameter. What is this that we are looking for? Is this a proportion problem or is it a mean problem? So we're going to say we want to estimate the true mean weight of an Oreo cookie at a 95% confidence level. Okay, and if you want to here, you can say instead of the true mean, you could say mu equals the true mean and put that in right at the beginning. Okay, all right, the next part is going to be checking our assumptions. So remember, there are still 3 of them. So number 1, we're going to look for, was it random? Okay, and on the last test, I noticed a lot of people were checking for random and just writing check mark. We're going to say it was stated in the problem. Stated in the problem. I don't know what a check mark is as a grader. What does that mean? I got to say what it means. Stated in the problem, so we're good. Okay, the second one was the 10% rule. Okay, so I'm doing 10 little n has to be bigger than big N. And again here as well on the quiz, I saw a lot of people doing 10 times 36. And then just putting a check mark after this. No, you have to explain what that means. We're getting 360. So we can assume that there are more than 360 Oreo cookies in the universe. Then it gets a check mark. Okay, and then the last one we have to check is normal. Okay, so again, this is just, do we know it's going to have that general shape of that curve in the middle and the tails on the outside? It's not saying it's a Z or a T, it's just saying that it has that general shape, and that remember that if the sampling is big enough, they're going to be interchangeable anyway. Okay, so the first thing I'm going to check is, did they say the population? No. Did they give us central limit theorem? Yes. So we have 36 is greater than or equal to 30. And again, don't just put a check mark after this. You say it works because of central limit theorem. You're explaining why it works. So we can assume normal. All right, on to the next one, which is the name. So for the name, we are going to go with, this is a 1 sample. Again, I'm not comparing like 2 different packages of Oreo cookies to each other. So this is a 1 sample. It is going to be a T interval. So it would have been a Z interval if they would have given us the standard deviation of the population, that's sigma. Okay, it's 4 means. And this would be a good place to show degree of freedom. Is 36 minus 1 is 35. That should show up somewhere. 95% confidence should show up somewhere on there as well. All right, then our next one is going to be the interval. Now we get to actually calculate it. So we can start with the formula, which would be x bar plus or minus t star times standard deviation of x over square root of n. Okay, then we're going to go ahead and put our numbers in place. So we're going to say we have 11.3921 plus or minus. I've got to go find the t star score. So a t star score for a 95 is going to be half of 5%. right? So if I'm going to use the table, I'm going to look for 0.025 with a degree of freedom of 35. If I use my calculator, I'm going to do inverse t of 0.975. And again, that's just to make sure I get the positive t versus having to switch it. So inverse t of 0.975, and we have 35 as our degree of freedom. And in my calculator, I am getting a t star of 2.030. So t equals 2.030 t star. All right, and then my standard deviation is the 0.0817 over my original n. This is not degrees of freedom, this is your original n, so 36 was my sample size. All right, and then I'm going to calculate everything after the plus minus. So I'm going to get 11.3921 plus or minus. Go calculate all of that. And I'm going to get 0.0276. So here is my interval. I'm going to do the low amount and then the high amount. So I'm going to subtract 0.02 and then I'm going to add 0.02. So when I subtract, I get 11.364. And when I add, I'm going to get 11.420. Okay. All right, so conclusion. This is the one where we do the conclusion statement in context. That means I've got to be talking about means and I've got to be talking about Oreo cookies. But our standard setup is still the same. We are 95% confident that the interval that we just found, that the interval from 11.364 grams to 11.420 grams captures the true, and then you're back to whatever you wrote in P, the true mean weight of an Oreo cookie. Okay, yes, you have to do all this writing for these. It is not just the mathy parts. It is not just check marks. It's communicating to the reader how you got your answers, okay, and what that answer means. Good? All right, on to the next part. We'll put a little smiley face, got that part done. On to the next part. It says, on the packaging, the stated serving size is 3 cookies, and they say that that's 34 grams. Does the interval in part A provide convincing evidence that the average weight of an Oreo cookie is less than advertised? So what are we going to do here? We're going to go figure out how much that would be for one cookie, right? So if I took my 34 grams and I divided it by 3, I would get 11 1/3. So I'm going to say 11.33 grams. So the next thing I'm going to check is that within my confidence interval. My interval went from 11.364 to 11.420. Remember, the interval is where we think the true actual weight of an Oreo cookie is. Well, their own box is saying it's less than that. So that's a problem, right? Or is it? So we think the true mean weight is, so we think the true mean weight is between 11.364 grams and 11.420 grams. And the box claims a cookie weighs approximately 11.33 grams. Okay, so if Oreo is saying they're 11.33 grams and we're getting by our sampling that it's more than that, are we happy or sad about that? We're pretty happy, right? We're getting a little bit more Oreo cookie than what they're actually stating I should be getting. So they say, does it provide convincing evidence that the average cookie weight of an Oreo cookie is less than advertised? Yes, it's out of our interval range, so it is looking like, okay, it's looking like the Oreo cookie in the advertisement is less than we thought it would be. Does it provide convincing evidence that the average weight of an Oreo cookie is less than advertised? No, we're getting information that the Oreo cookie is actually more than advertised. So we do not have convincing evidence that the average weight is less than advertised. And we want to tell them how we got to that, less than advertised. Because our sampling showed a larger weight than advertised. So we don't have evidence to say they're doing less. We have evidence to say they might actually be doing more than advertised. Now, this is kind of silly, but let's say you were following a diet and you're reading the box and you're thinking, hey, that's 11.33 grams, that's so many calories, and then we do the sampling. Well, they might be underestimating their calories by a little bit, right, than what we're finding. We might be finding that the cookies are a little bit more than what they advertise, and a little bit more usually means a little bit more calories. But as far as their question goes, does it provide convincing evidence that the average weight is less than advertised? The advertised is the 11.33. So we are not getting less than advertised. We're actually getting more than advertised. So we don't have convincing evidence. All right, that's it for this one. We'll see ya.